Okay, I want to find the maximum shear stress in a beam such as this. Again, what's driving the equation is tau equals VQ over IT. And the first thing I need to do here is I need to figure out exactly where and what the maximum shear force is. So I'm going to call this one A, call this one D. Again, I'm going to figure these guys out. Right at the center of this guy, I've got 900, which is the 150 times 6. At 1/3 away, right here, it's going to be 1/2 base times height, so that should be 600 for the triangle. 1/2 base times height should be 600. So if I go ahead and I sum the moments about A, I get -3 times 900 minus, that would be 6, 2, that'd be 8, and then another 2, that'd be 10 times 600. And then 14 times D equals 0. From that, I can find that D equals 621.4, and then A, because I know that the total downward has to be 1500, A then has to be 878.6. So if I draw the shear diagram as a function of x, it's going to start over at the A at 878.6, and what it's going to do is it's going to follow a straight line slope because of the distributed load at a slope of 150. So when I get out to 6, it's going to be a total of 900 down. So it'll just barely cross right here at about -21.4. And I get that because, again, it drops 900 in a straight line over the course of those 6 feet. Then it follows a straight line until it reaches the triangular load, which will then create a parabola, which will continue to go downward on this guy. And it'll ultimately go down 600, and it'll follow some path kind of like this, where it goes down to 621.4, at which point it'll jump back up because of D being 621.4. So V max is right here. Okay. Now, we know that the maximum shear stress occurs right at the neutral axis. Okay. So I'm looking at this area here right above that to find Q, where Q again is the centroid of that guy times the area of that guy. So the centroid of that guy, okay, is going to be, so the location, I've got a T there, right? So I've got 2 triangles. So the first one will be half of the 3, so it'll be 1.5 up, times its area, which will be 0.5 times 3. Then I'll have the guy on the top, which will be 3.375, its location, right? Because I go up 3 and then half of the 0.75. Again, that's from the neutral axis, and then that's going to be times 0.75 times 4. And then I divide that by the area, which is 0.3 times 3 plus 0.75 times 4. And I don't actually have this number here, but I can then find the area, which is just going to be the denominator of that guy. I screwed something up. This should be a 0.5. Sorry about that. Okay. So then the total area of that T would be 0.5 times 3, and then plus 0.75 times 4. Oops, that should be a 5. That should be a 4. Okay. And again, I don't have these exact numbers, but I do know when you add them together that you get 12.375 for Q. Okay, so I'll let you do the calculations on your own and prove that to yourself. Now the last thing that I need is I. Okay, And that's going to be the moment of inertia, the whole thing. So what I'm going to do is I'm going to take the whole, because I don't want to deal with the parallel axis theorem. So I'm going to take the entire rectangle, which will be 1/12 4 times 7.5 cubed. That'll be the whole rectangle. Then I'm going to subtract off the two smaller rectangles on each side. So that's going to be minus 2 times 1/12, and then that will be a base of, so it's 4 minus 0.5, so 3.5 of that is 1.75, and then its height is 6 cubed. So again, I subtract off each of those, and what I'm left with is I, which is going to be 77.625. Now, of course, T is just the thickness of that point, which is very simple. It's 0.5. So now I can find the maximum shear stress, because the maximum shear force is at 878.6. Q is 12.375. I is 77.625. And T, T, the thickness is 0.5. From all of that, I find that the maximum shear stress is 280 psi. So again, using that shear diagram to find where the maximum shear force is probably the toughest thing here. Everything else is pretty straightforward, finding centroids and moments of inertia and things of that nature.